good afternoon, or morning, depending on where you are located, and welcome to today's webinar. My name is Mark Musitano. I'm a Senior Sales Engineer here at DFR Solutions. On the line with me today is Michael Blitzeau, and he will be presenting on common mistakes by electronic design teams. This is part 2 of a two-part webinar series on this topic. Last week's webinar was hosted by Dr. Craig Hillman, who is the CEO of DFR Solutions.
Good afternoon, everybody. Like Mark said, this is the second part of common mistakes by electronic design teams. Just really quick, some background about DFR Solutions. We are one of the top 50 fastest growing companies for in this field. We offer a variety of services, everything from finite element analysis, failure analysis, root cause investigations, circuit analysis. We can also do test to spec. We can design mechanical test fixtures, test coupons. So we are an end-to-end quality and reliability company. This second part is regarding mechanical part selection. In the first half, Dr. Hillman, he went over make versus buy, sizing your box with regards to thermal issues. He went over electronic component selection, derating, power sequencing. This part we're going to focus more on mechanical part selection, probably just touch on the most common areas where we see issues. And perhaps the number one cause of issues that we see is cables and connectors. It's one of the most common failure locations in most electronic systems and embedded systems, of course. The primary some issues we see, especially with has to do with red phosphorus, flame retardants in connectors and in cable overmolds. We're seeing this more towards in the commodity type cables and connectors, things that people will buy off of Amazon or eBay or dx.com, you know, the ones where you're not sure where they came from. Just be aware that some of those plastics may contain red phosphorus, and if you put them in a harsh environment where there's a lot of heat and moisture, after 2 to 4 years in the field, we see that the plastic has dissolved and phosphoric acid has leaked out and corroded the contacts and traces on the board. So just be aware of that issue. So it's best just to not spec those kind of connectors, or just be aware of who your supplier is and what plastic they're using. Here's some simple DFR rules for connectors. Your power and ground should be separated from each other. That's just so you don't get tin whisker formation between the two high potential areas. You should shroud your connectors. You want to avoid blind insertions. This is really critical with mezzanine style boards where you're plugging modules down. You want to have alignment features. Hopefully, it's most helpful to have those alignment features on the connectors so that the user can feel the two connectors aligning and pushing them together. You run the risk of bent pins or busted connectors if the user or the assembler cannot positively feel the alignment. You should always have some sort of retention. Connectors and cables that are inside a box should have some sort of strain relief, especially if you're in a vibration environment. Also, you don't want to use connectors or cables that are not typically used internally in a box. Sometimes we've seen where people use Ethernet connectors to hook modules together inside an electrical device. Those connectors are not meant to be internal. They do not handle vibration well, and you're just asking for problems. So when you're doing your connectors, you're going to want to be selecting a type of plating. The least expensive is tin. The more expensive, of course, is gold. Gold is good for high-speed digital connections. It's good for if you're in a corrosive environment. It's also good if there's some sort of motion going on, if it's, like it's vibrating. If you pick a connector from a well-established or well-known supplier, you probably don't even have to worry so much about your material specifications, your Molexes, your Samtec, your TE, your Amphenol. They're all pretty good. They're all going to have well-defined, you're going to be able to pick what, by part number, what thickness gold you have. If you go with a lesser-known supplier, you're going to want to specify your thicknesses just to make sure that they're going to be meeting those thicknesses. The other choice you're going to have is tin. Tin is great. Tin works fine in certain applications. If you'll see tin-plated connectors in a lot of your appliances, they're using these because A, they don't have to go through as many insertions, and B, they're cheaper. So if you don't have to go through that many insertions and it's more of a power and high voltage style signal, tin works great. There's a few drawbacks. You cannot use it above 100 degrees C. And you definitely do not want to mix your platings. You do not want to mix a gold-plated connector with or contact with a tin-plated contact. What happens with that is the gold and tin form a intermetallic together. They actually fuse a little bit together, and then if there's any motion, it rips the gold plating right off the connector, and you get oxide, and it leads to early failure. So that's one portion. Now, you're also going to have to select, when you're doing a electronic system, you have to select what kind of housing you're going to use, whether or not you buy a housing off the shelf or you're going to design a housing. Essentially, you have two choices, that being of a plastic housing or a metal housing. With your plastic housings, there's a few design concerns, which I'll go over. And with your metal housings, there's a few other concerns that you probably should be aware of also. Probably the most area of concern with the plastic housing is your boss design, and that's because they tend to be a failure point, primarily because they're not designed correctly. They're one of the more critical portions of your enclosure because they hold everything together. They hold your board down. They probably sometimes will hold the box together. Primarily, most common mistake is the inner diameter is too large for the self-tapping screw if you're using thread-forming screws. You got to be aware that if it's a slipperier plastic, like a polypropylene, you're going to want the pilot hole has to be smaller. You also have to be careful that you take draft into account when you're designing your boss, because the boss diameter should be around 1.8 to 2.5 the diameter of the screw. If you're right on the edge, let's say you're at 2, and you don't take a draft into account when you send your plastic housing to be the design to the molding house, and they design the tool, they may add draft to all the external surfaces, and you could end up with a boss that's too narrow up at the top, in which case it'll crack easily. Some other common issues. You need to make sure that the thread engagement is sufficient enough, especially with the thread forming screws. Sometimes instead of a thread forming screw, you may use a brass insert in the boss. The key with the brass inserts in your bosses is that you want to make sure that the bearing surface that's being screwed down onto it is against the brass and not against the plastic. If you don't mate up against that brass surface, what happens is the screw actually pulls the brass insert out of the plastic, and this is called insert jacking. So I've got a couple images on the screen of what is a good insert installation and what is a poor insert installation. The one that says bad you'll see that the insert is actually suppressed down into the hole a little bit. So what's going to happen is as you tighten that up, it's going to get pulled up, and that will cause it to become loose. Another issue of concern with plastics is notch sensitivity. This really just comes down to making sure you have no really sharp interior corners. The more durable plastics, like your acetals or your Delrin, and some of your polycarbonates, and also if you have a high mineral load in your plastic, which is made really stiff, this becomes critical. For example, the piece I show here was made out of acetal, which is almost as strong as some metal, and yet, the unit was dropped and it just totally broke apart because of a sharp interior edge there. Also, when you're picking plastics for your housings, you have to be aware of the environment that plastic's going to be in. Some plastics are sensitive to temperature. They soften. So if you think that your usage environment may see 80 degrees C, you're okay with ABS. If you go above 80 degrees C, you're going to have to pick a higher temperature plastic, possibly a polycarb. Yes, ABS is cheaper than polycarb, but if you're going to be up at that higher temperature, you're going to have to go with a higher temperature plastic. You also have to be aware that plastics do not withstand UV that well. You'll have to make sure that there's UV stabilizers added to the plastic so that it can be exposed to the UV and doesn't end up discoloring or getting surface cracks on it. And then there's a phenomenon called environmental stress cracking, which is a combination of residual stress in the plastic and a surface interaction with any type of liquid that gets on it. This is usually most primarily seen in polycarbonates. It has been seen in ABS. It's more significant of a concern if you're in an industrial application or maybe an outdoor application. I've seen bosses crack because bosses inherently have a residual stress because you're putting a thread-forming screw in it that causes the plastic to be under a state of stress. It gets a surface contaminant on it, and that is enough to cause it just to crack. So then, that's just some of the concerns with plastics. So if you selected metal, it's probably because you needed something durable. You may have had to have some kind of water resistance or maybe waterproof it. So you're going to have to, most likely, you'll be doing some sort of gasketing. This is a case of using a flat gasket. You can also use O-rings or form-in-place gaskets. With flat gaskets, this happened to be a metal enclosure that had an LCD screen, which is very common. It was a textured gasket. It passed all its IP54 ratings, yet because the environment was actually a salt saline water that was getting on it, the gasket failed just due to a phenomenon called salt jacking. It's where where your liquid dries out, leaves salt crystals. The salt crystals expand, and it creates a path for the liquid to ingress into the enclosure. So just be aware of what your actual environment is going to be. Another concern would be if you have a metal housing, it's probably industrial, it's probably got a lot of heat, and that's why you picked metal. So you're going to be trying to get that heat out of the box. You're going to have some choices with how you get that heat out. One very common choice is the silicon gap pads. Just be careful with them. If you overcompress them and you put them in a sealed environment with a lot of heat, they will outgas. And that outgassing, if it can't get away from the pad, will attack the pad itself, and it's called reversion. The oil, it breaks the pad down, and silicon oil is released. That silicon oil loves to spread over everything, it readily leaks through any type of seal that you have, and makes a nice oily sheen all over your product. You also want to be careful that if there's any optics inside the box, that you don't use a silicone thermal interface pad. You can avoid this by using the cast-in-place silicon thermal interface material. There's also non-silicon-based thermal pads. So the final topic we'll touch on as far as metal housings go are constrained PCBs. Usually it occurs, you get this nice milled housing because you want it nice and rugged. You want to get as much thermal interface between the housing and the board. So you stick a bunch of bolts through it or screws. You've now made it such that the board cannot expand and contract because there's a CT mismatch between aluminum and PCB. The board is going to want to expand and contract at a different rate than the housing. If it cannot do that, it's become what we call an overconstrained PCB. It causes localized buckling under components, especially around mounting holes, causes the solder joints to fail. Ways to mitigate this is don't overdo the connector, don't overdo your fasteners, and if you have a lot of fasteners, make sure your tolerances are such that the board can float around those mounting holes a little bit. You don't want them so tight. You don't want it where you're forcing a screw in and it's right up edge to edge against the hole. You got to have some float. Shoulder bolts or slotted holes work great. Even just a slightly larger hole with a dual washer stem works well also. You got to let that board be able to release some of the stress on it. Now we'll just touch on some guaranteeing reliability. So how do you design your system? Do you design it to pass a test? You design for reliability. Historically, a lot of embedded system designers have not performed any testing. And when they do perform a test, it's because it's specified for the customer, by the customer. Sometimes the customer will say, hey, I need it to run at 80 degrees C and minus 40 degrees C. Can you guarantee that? So your electrical engineer, he'll put that board in a thermal chamber, set the temperature at those two extremes, and make sure everything runs. And if it passes, great. However, that's not really that tells you electrically it's going to run. It doesn't tell you anything about how reliable your product's going to be out in the field. Not every failure mode can be tested for. And if you are seeing failures, then it's too late. There's just so many modes of electronic system can fail, between the solder fatigue, board crack, capacitor cracking, electrolytic caps failing. You can't test for all of it. So what we recommend is you design for reliability based on a few rules of thumb and a physics of failure to identify the wear out risks. A couple rules of thumb, just a few of them. Constant temperature. If you're not going above 40, a constant temperature is not an issue. If you are going above 40, yes, you have to start worrying about being at the constant temperature. For example, 85 degrees C, 2,000 hour electrolytic cap, if it's running at 85 degrees C, it's not going to last 5 years. Okay. There's also an issue with solder joints. If your solder joints are running at 75 to 85 degrees C, what happens is they form the intermetallic starts to grow and the joint becomes very brittle. It can now be more susceptible to shock and vibe damage. For temperature cycling, if you're in a low power outdoor environment, it's not much of an issue. Your typical environmental swing throughout the day is about 25 degrees C. That is sufficiently low where you wouldn't have to really worry about plated through hole fatigue or solder joint fatigue. It becomes more of a concern when you start stacking up different temperatures on it. So if you have thermal loading, Now your deltas can see 40 degrees C. Okay. If the device now has to go through power cycles, that becomes another issue. An automobile under the hood of an automobile. If a person turns the car on a few times a day, it's sitting out in the sun, that's a very harsh environment. You now have to start worrying about your solder fatigue, your plated through hole cracking. Vibration rule of thumb. Design your board to be about 2x times greater than the highest energy peaks in the vibration spectrum that you think the device will see. A good rule of thumb is your natural frequency for your board should be around above 250 hertz. If you're around 250 hertz, chances are most things in the field that your box will see or your board will see won't meet that. So you use those rules of thumb to identify the potential risks. And you really only want those to apply to components that could wear out. And then your other approach is use physics of failure to calculate lifetime of parts that also could wear out. So this tells you what is your actual risk. So physics of failure, you would, for solder fatigue, physics of failure for plated through hole, cracking, that type of thing. If you have, for example, if you have a very harsh temperature environment, you may have to mitigate that somehow. You may have to corner stake. You may have to underfill your BGA, that type of thing. So here's a list of what typically wear out in electronics. Aside from your solder fatigue and bending, these are other things that can go wrong. Ceramic capacitors have an oxygen vacancy migration issue that they can have. You got tin whisker formation. Anything electromechanical relays. You got to be careful. Silver-based plated boards, components. Sulfur environments, they're very susceptible to. So for an example on wear out of ceramic caps, this is more applicable to your small caps that have a very large, for their size, a relatively large capacitance value. And as you can see, as the temperature goes up, their useful lifetime is severely affected. And we talked about solder. I've mentioned solder joints already. The reason solder joints are now more in the forefront as far as failure issues is because the industry has moved away, well, hasn't moved totally away, but people want to move away from your gull wing leaded devices. And this is primarily due to cost. You get rid of that extra piece of metal and you have a cheaper part. Unfortunately, that gull wing is a compliance adder. It adds flexibility to the part. It takes in some of the CTE mismatch between the part and the board, and therefore you have a longer life. So as you move away from those the leaded package and you go to BGAs and then you go to the QFN and then you go to even the smaller CSP, where the die is almost as big as the part, your CTE mismatch between the part and the board is all taken in by the solder. There's nothing decoupling that motion or that the stress on each other, and that's why the life of these guys are a lot less. So you're typically in this cycle to failure from -40 to 125. A quad flat pack, gull wing leaded quad flat pack can survive 10,000 cycles. And then you go to the lower end of the extreme, your flip chip CSPs, less than 1,000 cycles. So 10x order of magnitude change based on just the structure of the component. So here's some of all the myriad equations that are used to do these physics of failures. However, if you can grasp some understanding, it just puts you a leg up over your competitors. There's some physics behind what you're saying on your product. So if you can do a plated through-hole cycles to failure analysis, that's just one extra thing that sets you apart from your competition. So in conclusion, stay agile. Yes, you can mitigate your risk, but you shouldn't be so wrapped around it that it impedes the product development. You got to just work with it. You mitigate the risk. You show some background behind what you've been designing. You show that you've done the research where you can say, hey, we studied this package. This package can survive, 10,000 cycles of this thermal profile. It's just that much better gives a level of comfort to your customer. Improve your processes and tools. Add some of those rules of thumb. Add the rule of thumb based on, maybe your capacitor sizing or the thermal load. I think Dr. Hillman talked about thermal, sizing. It helps. And that wraps it up.
If you have any additional questions, my information and Michael's information are on screen now. Feel free to write it down and shoot us an email or give us a call. If you have any more technical questions, Michael's going to be your guy. And then if you want the copy of this webinar, feel free to email me and we can send that out to you right away. If not, it'll be up on dfrsolutions.com relatively soon. And then Michael, if you could go to the next slide, please. And I just wanted to bring this up as it is coming up fairly soon. We're having our Design for Reliability conference, the Sheraton Inner Harbor Hotel in Baltimore, Maryland. You can sign up, or if you're interested in signing up, just please go to dfrsolutions.com. It will be the first link you can click on. And you're more than welcome to sign up for that and come out and see us if you have the time on March 20th. If you're a Sherlock customer, we're also going to be running some Sherlock trainings as well, and that information is on the website. So just wanted to bring that up for everybody on the line if you're interested and possibly in the area during that time. So with that, I'm not seeing any additional questions. So we're going to go ahead and close out the webinar. Thank you once again, Michael, and to all, have a great day.